All right, guys, it's time for some fun with math. And so today, what are we going to do? We're going to cover this little lecture activity on sequences and series. And so don't forget to upload this by midnight on Friday. And of course, if you have any questions, you can always email me right here. All right, so let's just get started. We first want to make a table and find a formula for each of these sequences. So remember, a sequence is just a list of things. And so in this case, it's a list of numbers. So we have this 1, 4, 9, 16, 25, and 36, then dot, 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 that pattern should continue. So we need to figure out that pattern. So if you can look at this and tell me what a sub n is equal to, then great, then write it down. But if you can't, you might want to try this, and I think this is good no matter what. So you just make a little bit of table here. And so you have the first term, the second term, the third term, the fourth term, the fifth term. And the first term is a 1, the second term is a 4, the third term is a 9, the fourth term is 25. Oops, I missed one. The fourth term is 16, and the fifth term is 25. So you're just kind of counting off like first term, second term, third term, fourth term, fifth term, and sixth term. And so I made the tables a little bit small, so maybe I won't put the sixth term in there because I think I can figure out the pattern from here. So if you take a look at this, it's kind of like, how do you get a 2 or a 4 from a 2? And so how do you turn that to? And so it's probably, that looks like 2 squared to me. And the pattern then, yeah, it continues. That's 3 squared. And so it's kind of like a guess and check a little bit. And so this is 4 squared. And so this is 5 squared. And so if you put an n here now, well, if it's 5 squared, so it's n, it should be n squared. So I'm thinking here, a sub n, the formula for my sequence is just n squared. And you can test this if you want. Notice if you plug in 6 here, you do get at 36. So it certainly checks. And now once you have a formula, what's nice is you can find any term in your sequence. So if you wanted, like, for example, a sub 100, the 100th term in your sequence, it would be equal to just 100 squared, whatever number that is, right? Which you can figure out with the calculator if you want, or you can probably do it by hand. All right, let's move on, though. We have more and more of these to do. So let's take a look at B here. So let me go down a little bit. Maybe not so far. All right, so for B, here is our sequence. And again, if you can just write down the formula, go ahead. If you're, and actually part of this you could probably write down. So notice you have 3 halves, 3 fourths. So always on the top, we have the number 3. So there's definitely going to always be a 3 on top. And then what goes on the bottom here? So you have a 2, a 4, an 8, a 16, and a 32. Well, if you can figure that out, great. If not, then come over here and we'll just write these down. And so I have n, and I'll do b sub n this time. You could do a sub n again if you want to. And so, you have your first term, your second term, your third term, your fourth term, your fifth term. And so what do I have here? I have 3 halves. I have 3 fourths. I have 3 eighths. And I have 3 16ths. I'm kind of running out of space here. There's 3 16ths. And finally, I have 3 over 32. And so we want to figure out what happens when you plug in n. And clearly, we can see that you have 3 divided by. And so the question becomes, what is this thing in the denominator? So I'm going to circle them so we can kind of highlight them a bit. And so notice if you have a 1, you get a 2. If you have a 2, you get a 4. If you get a 3, you get 8. So each time they're going up by times 2. So, this one's like 3 over 2 to the 1. This one here, the next one's like 3 over 2 squared. That works. And then 3 over 8 is like 3 over 2 cubed. So it looks like, if you have a 3, it's just 2 to the 3. So if you have an n, I bet it's 2 to the n. And so this would be 2 to the n right there. And you can test this if you want. So let's just test it real fast. So what would be to the b sub 5 be, the fifth term of your series? It would be 3, 2 to the fifth, which would be 3 divided by, and it's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And it checks because that's the fifth term of your sequence. Hopefully I didn't say series there. It's easy to get the 2 mixed up. So remember, a sequence is a list and a series is a sum. Okay, let's do the last one. So for the last one here, we have this sequence. And this one's a little trickier. So, we want to figure out, we'll call this C sub n. We'll just give them different names, A, B, C. You can call it A sub n if you want to too. And so you're definitely dividing, because notice in each of these you're dividing. So it's like, oh, great, I know I'm dividing. One of the tricky parts of this one is you're also doing something called alternating. You're going from minus to positive, minus to positive, minus to positive. So you're definitely going to have like something up here that's going to make it alternate. If you're not familiar with how you make things alternate, it might be kind of tricky to figure this out, but we've seen a couple of these now. So how do you make it alternate? Basically, you just put a -1 into the nth power, and that'll make it alternate. The only thing you have to worry about is make sure it alternates correctly. So notice that first term here, right? So that first term, so you remember first term, second term, third term, fourth term, fifth term, the first term is negative. So notice if you do plug a 1 in here, you get -1. So it starts out. If you plug a 2, then it's positive. The 3 is going to be negative again. So that's going to make it alternate. And then the tougher part might be, once you see that, is what's down here in the denominator. So 2, 5, 8, 11, and 14. So let's go over here, and maybe I'll remake this little table here so I can make it a little bit bigger. And so I have n, and I have C sub n now. We have the first term, the second term, third term, the fourth term, and there's the fifth term. And then so it's -1/2, and then it's +1/5, and then it's -1/8, and then it's +1/11, and then it's -1/14. And we already said that for n, we do know it's divides, and it's -1 to the n. That makes it alternate. And so the tricky part, though, is trying to figure out what goes down here. 2, 5, 8, 11, and then 14. Now, hopefully you can see the actual pattern here. So 2 to 5 to 8 to 11 to 14. So what are you doing each time? You're just adding 3. So basically on this, the 2 to 5, that 5 is a 2 plus 3. This 8 is a 2 plus 3 again, so 3 times 2. And this 11 is a 2 plus 3 plus 3 plus 3 one more time, so 3 times 3. And finally, that 14 is just a 2 plus, and you add one more 3, so it's 4 times 3. Oops. Let's do it like this. So here it's 3 times 4. So 3 times 4. And so when we get up here, so we're just adding 3 each time. In fact, you can do this one. This is 2 plus 3 times 0. We'll put a times 1 here. So you can see the pattern each time. So it's very clear each time what's happening is you have a 2 plus, a 2 plus, a 2 plus, a 2 plus, a 2 plus. So down here, I'll write 2 plus. And then you always have a 3, a 3, a 3, a 3, a 3 in the form. So in the formula, have a 3. And then times, now here's the tricky part. And so notice, if you have the first term, you have a 0 here. The second term, you have a 1. A 3, you have a 2. A 4, you have a 3. A 5, you have a 4. So if you have n, you have 1 less than n, so times n minus 1. And of course, you can clean that up a little bit. So over here, maybe we'll do that. So I have 2 plus 3 times n minus 1, which is really what? That's 2 plus 3n minus 3. We just multiply through by the 3 here. And so that's going to be equal to 3n, and then 2 minus 3 is a minus 1. And so now I know down here I have a 3n minus 1. And I can check it. So just for fun, let's do C sub 5. So the fifth term in our sequence is -1 to the 5. And then divided by, this would be 3 times 5 minus 1. And so I get a -1 on top because it's an odd power, and it's -1 to odd power is going to be -1. On the bottom, I get 15 minus 1, which is 14. And so, yep, that's definitely the fifth term. So it checks. So there's my nice looking formula for that sequence. And what's nice again about a formula is now you can find any term in that sequence. So you want the 1,480th term, you just plug in 1,480 for n, and I'll give it to you. All right, so that's a nice little review of finding formulas for sequences. Let's go down here to number 2 now. And so in this number 2, we have several things we want to do. So let's make sure we read these directions here. And so what we want to do is just write out the first 3 terms for each sequence, and then use the definition of convergence, so basically run a limit on it, to determine if the sequence converges or diverges. So we're now going to practice using formulas. And so for this one, we're just going to write out the first few terms. And in class, you guys did tables, which I really like tables, just because I can give you lots of partial credit for these types of things. And so, the first 3 terms, so not too many, so 1, 2, and 3. So you just plug in 1 into this formula. And so you basically get what? So 5 squared divided by 2 to the 1. So that's equal to 25 over 2. Now we'll plug in 2, and we get 5 to the, so 2 plus 1, which is 3, over 2 squared, which is equal to what? 125 over 4. And then finally, we'll plug in the third 3 into this thing. Oh gosh, it's getting kind of big. Maybe I don't have my calculator out here. Maybe I should get my calculator out just for the heck of it, because there can be some problems up here later on. We might want to check with our calculator. So let me find my calculator here, wherever it's at. Give me a second, guys. Here's my calculator. Let's see. There we go. Oh, perfect. Okay, here we go. So here's my little calculator right here. See if I can make that a little smaller. Great. All right, so I kind of wanted this because now when I plug in 3, I'm going to get what? So 5 to the, and we plug in 3 here, it's 3 plus 1, which is 4 over 2 cubed. Now 2 cubed I can do in my head. That's not a big deal. That's an 8. But 5 to the 4th is a little bit tricky. So I want to say like 625, but I'm just going to check it real fast. Once we get to these bigger numbers, it's easy to make silly mistakes. And so 4, oh gosh, I'm struggling here, guys. All right, so 4, still at daylight savings. It is 625. All right, so the old brain's still working on for me. So 625. All right, so there's the first 3 terms in that sequence, and let's just list them. So we'd write 25 over 2, comma, 125 over 2, comma, and then 625 over 8, and that wasn't a 2, that should be a 4 right there, and then dot, dot, dot. So continuing that pattern forever and ever. Great. And so now what do we want to do? We want to use the definition of convergence to determine whether this sequence is going to converge or diverge. So let's run a limit on it. So limit as n goes to infinity of 5 to the n plus 1 over 2 to the n. Now here's where you have to be a little bit careful. You can test it by plugging in infinity. So 5 to the infinity plus 1 over 2 to the infinity. And so I'll put quotes around this because it's kind of me thinking here. And so that's really infinity over infinity, which is an indeterminate form. And we talked a little bit about this one in class. You can try to use L'Hopital on it, but it doesn't really make it better. In fact, it looks a little bit worse in the end. So what you want to do on this is just do a little bit of algebra, because you can simplify this expression on top and turn this into, because what it really is a geometric sequence. And so we have here the limit as n goes to infinity, and we can rewrite this as 5 to the n times 5 to the 1, because you're just adding exponents there, divided by 2 to the n, which is really equal to the limit as n goes to infinity. And so we can rewrite this as 5 times, and we can put these guys together. And so we can write that as 5 divided by 2, all raised to the nth power. And so now when we take the limit, when we plug in that infinity, we can interpret it, and we know if this number here is bigger than 1, of course, it's going to go off to infinity. Of course, if it's between -1 and 1, it's going to head towards 0. And so this will be equal to then, well, let's not use yellow. Let's just plug in infinity. So 5 times 5 halves to the infinity. And of course, that's going to be equal to, well, that's going to be equal to infinity, because 5 halves is bigger than 1. So if you take 5 halves times 5 halves, it'll get bigger. Times 5 halves will get bigger again. Times 5 halves get bigger again. And so it'll get bigger and bigger. So basically, it'd be 5 times infinity, which equals infinity. So therefore, my sequence A sub n diverges really by definition, right? And you can even write by the definition of convergence if you want. Maybe we should write by definition of convergence. Right, so that's a nice little problem, and it's easy to kind of get that one to get tripped up on that wrong one, like we did in class. All right, we got a couple more of these I want to do with you guys. So let's take a look at B here. And so here's our next sequence. And again, we want to write out the first few terms. So now that we've done tables for a while, maybe I'll just kind of start writing things out, just plugging in 1, 2, 3, because that's what we would normally do once we get comfortable with these things. And so I'll just plug in 1, so I get ln, and when I plug in 1, I get 3 plus 1, and then plus an ln of, and I'll plug in 1 again, and I get 1 over 2. And then I'm going to plug in 2, and so I get ln of, and then I have 3 times 2, and maybe I'll start writing some of this out, 3 times 2 plus 1. It's always good not to think too much, just be kind of a little math machine in the beginning, and then step back and start to think as you kind of go through this. So I plugged in 2, and now I'll plug in 3, so 3 times 3 plus 1, and then plus ln of 1 over 2 times 3. And now as I'm doing this, then comma, dot, 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 my brain's starting to think about this a little bit more, and it's realizing, hey, that plus right there, I can turn that into multiplication. And so, really, this is the sequence ln of, and that plus means I can just do 3n plus 1, and then times 1 over 2n. So it's really equal to ln of 3n plus 1 divided by 2n. So that's kind of nice, and so I can take advantage of that. So that's going to be equal to ln, and then, of course, that's a 4. And so that's going to be 4 times 1/2, because there's my 1/2 there, comma, ln of, and then this right here is a 7, and that's going to be times 1/4, and then comma, ln of, and then this guy's 3 times 3 plus 1 is a 10, and that's times, and this is a 1/6, then comma, dot, 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 and that's going to be equal to then ln of, and that's a 2, right? 4 times 1/2 is a 2, and then comma, ln of 7 divided by 4, so that's just going to stay, that doesn't reduce. And then ln of, and then 10 times 1/6 is 10/6, or if you want to reduce it, it's just 5 over 3, and then comma, dot, dot, dot. And that's it. So that's the first 3 terms. And so, you don't have to do a table once you kind of get comfortable with these, but tables are nice. This does show quite a bit of work also too. So now what do we want to do? We want to see if there's an actual limit here, if it converges or diverges. So we're going to run a limit on this thing. So limit as n goes to infinity. And we're going to use this form here since it's equivalent. So of ln of, oh, well, actually, let's just do this for fun. I'm going to do this for fun since ln of 1 over 2n. Just so you guys can see what happens when you plug in infinity. I think we can get some practice out of here. So what happens when you plug in infinity? So let's just think. You get 3 times infinity plus 1, and then plus ln of 1 over 2 times infinity on the bottom. I'll put this in quotes because I'm kind of thinking here. So basically, the idea is you're getting ln of infinity, and then plus ln, and then 1 over infinity is like 0. And now ln of infinity, as the inputs get bigger, ln gets bigger. So remember what the graph of ln of x looks like. So the graph of ln of x looks basically kind of like this. And it does have a vertical asymptote here at 0. So at x equals 0, you have a vertical asymptote. So as you go all the way out to the right here, the graph continues to go up, 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 up forever and ever. So it's going to be equal to infinity, and then plus, and then ln of 0, well, here's 0, ln of 0, you're going all the way down. So it's actually negative infinity. So what we get here is infinity minus infinity, which I don't know if you remember this, but this is another indeterminate form. It's like if you take infinity and take away infinity, what's happening? Are the infinities canceling? Is one infinity bigger than the other? I don't know. It's like either evening out somehow and going to a number. And so this, again, is another indeterminate form. And so when you have that, again, you have to change it into a L'Hopital type if you can. So basically the idea is you want to rewrite this somehow to get infinity over infinity or 0 over 0. So remember, that's the big idea for L'Hopital. If you get out an indeterminate type that's not a L'Hopital type, then what can you do? Well, usually you can manipulate it somehow and turn it into a L'Hopital type. And in this case, it's just a little bit of algebra, or in this case, the property of logarithms, actually. So remember, this is actually equal to the limit as n goes to infinity of ln of, and we already did it up here, and 3n plus 1 divided by 2n. And so now if you plug in infinity, what do we get? We get ln of 3 times infinity plus 1 on top over 2 times infinity on the bottom, which is basically ln of infinity over infinity. And that infinity over infinity is that indeterminate form that we can L'Hopital. Or actually, it's a little bit easier. So if you want to L'Hopital this, you can. So you just go on the inside and you L'Hopital it. But it might be easier in this case just to use some infinity arguments. So this will be the same thing as the limit as n goes to infinity of ln of, and we can cross off that 1 because you're going to infinity. So it's like 3 times infinity plus 1. Well, really the plus 1 doesn't matter. So it's going to behave like 3n on top, and you can keep the 2n on the bottom. And then we can write the limit as n goes to infinity. And of course, we can cross off the n's now. And so it's going to behave like ln of 3 over 2. And of course, the limit of a constant is just a constant. So it's ln of 3 halves. Perfect. So what do we just discover? Therefore, our sequence a sub n converges. We can even write down it converges to ln of 3 halves by the definition of convergence. Right, so that's nice. So that is a good example of a sequence that actually converges. All right, now I put an extra problem on here that we don't always do every semester because I know we struggle with these. So we always struggle with factorials because they're a little tricky. And really why you struggle with them is because you have to use inequality arguments, which are hard to come up with. So let's take a look at this last example here. Oh, we have actually one more, but let's take a look at this example here where I have a factorial. So there's my sequence c sub n equal to 7 to the n over n factorial. Let's write it out first. So our sequence here is what? So let's write out the first term. So it's just 7 to the 1 over 1 factorial. The second term, 7 squared over 2 factorial. The third term would be 7 cubed over 3 factorial. And then we'll just write dot, dot, dot. And of course, that'll be equal to 7. And then 1 factorial is just 1. And then comma. And 7 squared is 49. And then 2 factorial is 2 times 1. And then 7 cubed, honestly, guys, I have no idea what 7 cubed is. So I probably would just use my calculator. So 7 raised to the 3. You could do it by hand because you take 7 times 49 if you really wanted to, but 343. So 343. And then remember 3 factorial, it's just 3 times 2 times 1, and then comma, dot, dot, dot. And so this is going to be equal to, it's going to be equal to 7, and then comma, 49 over 2, and then comma, and then 343 over 3 times 2 times 1, which is 6, and then comma, dot, dot, dot. Perfect. All right, so there's our first 3 terms of our sequence. And now we want to find if it converges or diverges. And so on this one, it's tricky. So like I said, you have to use kind of an inequality argument. So you have to kind of go in there and play around with this guy. So let's just take a look at what 7 to the n over n factorial kind of means. And so that means you're going to do 7 times 7 dot, dot, dot. times 7, and you're going to do that basically n times. And then on the bottom here, and actually I might need a little bit more space. So let me write out the bottom first, because I'm going to need a little bit more space, because down here I'm going to have n times n minus 1 times n minus 2 times dot, 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 and then times 3 times 2 times 1. Right, that's what n factorial is. And so then I'll have a times 7 here, a times 7 here, then I'll write dot, 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 times 7 times 7 times 7. And so when you're doing this kind of stuff, you have to kind of know a little bit about how factorials actually work. So it turns out factorials even grow quicker than exponentials. So I kind of know this thing is probably going to converge and it's probably going to go to 0, because the factorials are just big. Like if you do 1,000 factorial, it's like 1,000 times 999 times 998, so on and so forth. Now 7 to 100 is a big number too, but that 1,000 times 999 times 998, they kind of dominate until they get down to 7, basically. So what that kind of means is that you can kind of look at some of these terms. In fact, you can kind of go up to where you have 7 here and a 7 up there, right? Because 1, 2, 3, 4. In fact, let me make that more obvious. So let me do a little math magic here if I can. Can I grab these guys? I don't know if I can grab that guy or not. Can I move him over? You can move it over a little bit. There we go. Hey, that's not so bad. All right, so there we go. And let me write out here 7 times 6 times 5 times 4 with a dot, dot, dot. And then I guess I don't need that dot, dot, dot. It's already got a dot, dot, dot there. And then above it here, I can write a times 7, a times 7, a times 7, and a times 7. And so what you want to see is that each of these guys are going to go together, right? The 7 and the 1, the 7 and the 2, the 7 and the 3, the 7 and the 4, the 7 and the 5, the 7 and the 6, and the 7 and the 7 go together. But everything over here, so 8 times 7, so all this stuff right here, this is a number that is always going to be less than or equal to 1. Why? Because the denominators are always bigger than the numerator by the way it's set up. So think about it, 7 over 8, right, is basically, yeah, it's less than or equal to 1, right? So it's 7/8. The next one would be 7/9, 7/10, and so on and so forth. So this will always be less than or equal to, you're left with a 7 over n over here, so 7 over n. You want to keep that guy because it's going to force you to 0. And then we have all these 7, so 7 times 7, 7 times, I guess. You have 7 to the 7, and then divided by 7 factorial. But that statement is always true because that thing in green is always less than or equal to 1. And so now what we can do is we can run a limit argument on this. And so we can take the limit as n goes to infinity of the left-hand side, so 7 to the n over n factorial. This will be equal to, and we can just rewrite the statement here, the limit as n goes to infinity. And we can write, 7 times 7 times 7 times dot, 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 and then times, the 7 to the 7th, basically. And then we have this n times n minus 1 times n minus 2. And we'll maybe put one more 7 here. And then dot, dot, dot times 8, and then times 7 factorial. So I'm just putting these guys all together. These guys are going all together here. And then this will be less than or equal to the limit as n goes to infinity. And then we keep this 7 over n right here. So 7 over n. And then remember, this guy right here, the numerators are always smaller than the denominator, so it's always less than or equal to 1 there. So we'll put a times 1. And then times, and then we have this guy left over on the very end right here. And so 7 to the 7 over 7 factorial, which is just some number, but we know what that limit is. So this limit is equal to what? What's just 7 times 7 to the 7? And then we have infinity on the bottom times 7 factorial. Well, guys, these are just a number on top and a number on bottom, but you have infinity, so it's going to be equal to 0, right? That bottom's going to keep growing bigger and bigger and bigger, and so it's going to force that limit towards 0. And so now, if this limit, of course, is less than or equal to 0. And of course, it's always positive, right? So 0 is bigger than or equal to that limit because if you want to call this a function, we can call it a function. So that function itself is always positive. So what we basically did is we squeezed it, and we squeezed it and took the limit, and both limits on both sides were 0. So it forces that thing to be 0 when you take the limit. So therefore, the C sub n's, the sequence C sub n converges, and it converges to 0, and of course is by the definition of convergence. Nice. All right. So that's a nice little problem. It's always a little tricky to do. Of course, if you change this a little bit, you make A sub n, you put the factorial on top now, it's going to diverge. It's actually going to go to infinity. And you can use a similar argument, but instead of having less than or equal to 1 in the middle, it's always bigger than or equal to 1 in the middle there. All right. Let's do this last one. So I threw this one on here because we've been practicing this. I thought, heck, let's just practice it one more time. And so let's write out the first few terms. So what happens when you plug in 1? So you get 1 over, and let's go slow, 1 plus 1 to the 1. What happens when you plug into 2 here? Well, you get 2 over 2 plus 1, quantity squared. And then let's plug in 3. So you get 3 over 3 plus 1, quantity cubed. And then comma, dot, dot, dot. And so what is that equal to? Well, it's equal to 1/2. And this one is 2 over 3 squared, so 2/3, and we'll square it. And this one's 3 over 4, and we'll cube it, dot, dot, dot. And so that's equal to 1/2, comma, and now we have 4/9, comma, and then 3 cubed is 27, and 4 cubed is 64, then comma, dot, dot, dot. So there's the first 3 terms of our sequence. It seems like it probably is going to head somewhere. It looks like the number's getting kind of big, right? But the question is like, where is it going to go? Is it going to go to a number? Well, let's just see. So let's run that limit on there. So limit as n goes to infinity of n over n plus 1 to the n. And so let's see what happens when you plug in infinity. Infinity over infinity plus 1, all to the infinity. And again, I'll put that in quotes because I'm kind of thinking here. And so basically on the inside, that's like a 1, basically. And it does behave like 1 because it's kind of linear on top and bottom. So it's going to behave like a 1 on the inside. And of course, you have infinity on the outside. And so that's one of those exponential types of indeterminate forms. So again, it's an indeterminate form. And it's one of those that in order for us to turn it into an infinity over infinity or 0 over 0, we have to undo this sort of exponentiation here. So the trick is to bring in e's and ln. So we're going to bring in this tool, so limit as n goes to infinity, that unlocks exponents basically. So we rewrite this as e to the, and then ln of n over n plus 1 to the n. And so what that does is that brings the exponent down in front here. So it'll be equal to the limit as n goes to infinity of e to the n times ln of n over n plus 1. And so now if you plug in infinity, in fact, I'm going to split this up a little bit. I'm going to call this basically e to the question mark, so we can make this a little bit easier to do, where question mark is equal to the limit as n goes to infinity of this guy, n times ln of n over n plus 1. So this is how I always do it in calculus 1. In calculus 2, sometimes I don't split it up, but it's nice to split it up. It just makes it a little bit easier to write down, I think. And so what happens when you plug in infinity now? We get infinity times ln of infinity over infinity plus 1. And again, this is just me thinking. And so I get basically infinity times, and then this is like ln of 1. And so it's equal to infinity times 0. So what we were able to do by using e's and ln's is turn this exponential indeterminate type into a multiplicative indeterminate form. So that's and also an indeterminate form. And now what we want to do is somehow take this guy here and turn it into one of these. guys. And we could easily do that by just doing a little bit of algebra. So this will be equal to the limit as n goes to infinity of what? ln of n divided by n plus 1, and then divided by 1 over n. And now you'll notice if you plug in infinity, you're basically going to get ln of 1 on top and 1 over infinity on the bottom. And ln of 1 is 0, and 1 over infinity is basically 0. So now it has the right type of indeterminate form, the one that we can L'Hopital. And so now let's do that. And so here, this is going to be equal to, and so how do we do L'Hopital? Well, remember, it's not terrible. You just take the derivative of the top, and so derivative ln is 1 over, so it's 1 over n divided by n plus 1, and then times the derivative of the inside. So remember, the derivative of the inside, it's a quotient rule, guys. So this is a quotient. And so it's just going to be low d high minus high d low, all over low squared, and away we go. So you're going to do n plus 1, and the derivative of the high function is just 1, minus the high function, which is n, and then derivative of the low function, again, is just 1. The derivative of n plus 1 is 1. And then all over low squared, so n plus 1 quantity squared. And then this is going to all be divided by the derivative of the bottom, because that's L'Hopital. Take the top, divide the derivative of the bottom. And remember, 1 over n is really just n to the negative 1. So when you take a derivative, what do you get? You get negative n to the negative 2. So it's really just 1 over, if you want, n squared. And so now we can rewrite this as being what? The limit as n goes to infinity, and we'll flip this guy. So write that as n plus 1 over n times, and on top here, you can kind of simplify. So you have n plus 1, and then minus an n. So the n's are going to cancel. And so we're just going to get a 1 over n plus 1 quantity squared. And on the bottom, you're dividing by a fraction, so we'll multiply by the reciprocal. So it's times a negative n squared over 1. And so this will be equal to the limit as n goes to infinity of what? So we'll have a negative n squared on top, and then times an n plus 1. Right? So you just basically have this times that. And on bottom, we'll have an n times n plus 1 squared. Oh, so some things are going to cancel here. So let's be the same thing as the limit as n goes to infinity of negative n squared divided by, and then this n plus 1 on top will cancel with one of these in the bottom. So we'll have an n times n plus 1 on the bottom. And if you want, you can write this out. So you can see basically they have the same power on top and bottom. So negative n squared on top, and then multiply through by n here, and we get n squared plus n. And so now I can L'Hopital this guy again if you want, because you do have infinity over infinity type form, but it's actually a lot easier. You can just cross off the n on the bottom if you want, because you're going to infinity. And so that's going to be the limit as n goes to infinity of negative n squared over n squared. And of course, then the n squareds are going to cancel. So it's just a limit as n goes to infinity of negative 1. And so that's equal to negative 1. And then be careful, because you're actually, that's not what the sequence actually converges to. The sequence actually converges to, remember, e to the question mark. So it's actually equal to e to the negative 1, or if you like, 1 over e. So down here, let's just zoom out a little bit. So down here, when I write my conclusion, I can say what? I can say, therefore, this d sub n converges, that sequence converges to 1 over e by the definition of convergence. So that's a nice little problem. Now, this is what's nice now is you can actually check your work a little bit. So if you want to, let's just take out our calculator and let's just plug in a really big number into that formula up here. So let's plug in 1,000 and see what happens. So 1,000 divided by, and then in parentheses, we'll put 1,000 plus 1. In parentheses for the denominator, in parentheses, because now we want to raise it to 1,000. So we're just plugging 1,000 into the formula to see what happens. And we hit enter, and that's the number we get out. And then the question is that like 1 over e? So let's do 1 divided by And then second ln is my favorite way to probably get to E. And you see, oh, those numbers are pretty close. So I'm thinking I did that right. That looks pretty good. So maybe I'll put a little check right there. Right, so that's a nice little problem. Or better yet, let's just put a little star, right? Since we got it and we checked it. Because that's a tough little problem. Okay, so that's for sequences. Now we're going to move on to series. So series, remember, is a little bit different. It's not a list of things, it's a sum of things. And so what we're going to do is we like to write it in this closed form here using that big sigma, which is actually a letter S, Greek letter S. But we're not just practice here just by writing out the first three terms so we understand what that notation means. And then we'll find the value of each convergent series. So I'm telling you that these series actually converge. So then we can find the value that they converge to. So in general, remember, it's really hard to tell if a series converges or diverges. And that's basically why we're going to spend the rest of the next couple of weeks basically trying to figure out doing techniques that can tell us whether a series is going to converge or diverge. All right, so let's just write out the first few terms here. And so notice it starts at 1. So we have the first term of the series. And so you just plug in a 1. So let's, 3, let's go slow. 1 plus 1 minus 1 over 3 to the 1. And then plus, now let's plug in 2. And so it'd be 2 plus 1 minus 1 over, that should be 4 squared. I guess I wrote a 3 there. It should be a 4. Let's fix that. So 4 to the 1. And then plus, and now we have plug in 3, so 3 plus 1, and then minus 1 all over 4 cubed. And then we just write plus dot, dot, dot. And then we can write what that's equal to. So that's going to be equal to, and it's 3 squared minus 1. So again, nice and slow, no reason to go fast. And then 3 cubed minus 1 divided by 4 squared. And finally, and I'm putting commas. That's a no-no. So easy to make these little mistakes, right? So right here, certainly shouldn't be commas. They should be pluses, right? So easy to turn series into sequences and vice versa, but we got to kind of keep them straight. And the next one would be a plus, and that'd be 3 to the 4 minus 1 over 4 cubed. And of course, plus dot, dot, dot. And so finally, that'll be equal to, and so 3 squared is 9 minus 1, so that's 8 over 4. And then plus, this one's 3 cubed minus 1, so that's 27 minus 1 is just 26 over 4 squared, that's 16. And then plus, and then 3 to the 4, well, that's 81 minus 1, so that's 80, divided by 4 cubed, which is 64. And so then plus dot, dot, dot. And of course, a lot of those, I guess, they definitely reduce, right? So that's going to be equal to, and so that's going to be a 2. So that's a 2 right there. This is a 13 over 8. And then plus, and that's an 80 over 64. Well, gosh, man, 80 over 64, what is that? That's a 40 over 32 and a 20 over 16. Oh, my goodness. And a 10 over 8. Oh, it's killing me. A 5 over 4. Crazy. Is that right? I'm skeptical. Right, I'm not quite sure. So when I'm like, let's just check it out. Let's just real quickly plug it in our calculator here. And so you can see what happens on each of these. So, if you put 3 squared, oops, that's not 3 squared. And that's not right either. So 3 squared minus 1. This one I think I'm pretty good on, right? That's definitely going to be an 8. And then divide by 4, that's definitely good. So we can check that real quick. That's no problem. The next term we can check too. So 3 cubed minus 1. That's not going to work. So 3 cubed and then kick it out. Let's use this. So it's harder when I use my hands there, like keyboard. So then minus 1. And then when I divide that by 16 4 squared. So that's definitely good. And so it looks like that. We can math frac it real fast. If you haven't seen that, that's nice to do. So it's definitely 13 over 8. We're good. And finally, 3 raised to the 4. And then minus 1 gives us that. Divided by 4 cubed. And 4 cubed is definitely 64. It looks like this, which is 5/4. My goodness, right? So that's definitely 5 divided by 4. So you can check that pretty quick too. Right, so it definitely works. So there you go. So there's the sum of the first 3 terms looks like that. But now we want to figure out what it converges to. All right, so how do we figure out what it converges to? So this one we've actually seen before. This is a difference of 2 geometric series. So let's write this down equal to, this is the sum and equals 1 to infinity. And let's just split it apart. So that minus, we can split that apart as 3 to the n plus 1 divided by 4 to the n. and then minus a 1 over 4 to the n. So you basically have the denominator to each of the summands above it. And then we can write that as equal to the sum n equals 1 to infinity. And we can take that sum basically through it. So it's the sum of this minus the sum of that. So it's the sum of 3 to the n plus 1 over 4 to the n, and then minus the sum n equals 1 to infinity of 1 over 4 to the n. So these summations are infinite sums in some sense, these series, they have a little bit of an algebra to them if you want. So it's like that sum can go through the difference. And then we can rewrite this guy as what? We can rewrite that as the sum n equals 1 to infinity of 3 to the n times 3 to the 1 divided by 4 to the n. And of course, still minus the sum n equals 1 to infinity of 1 over 4 to the n. And so now I can rewrite this as equal to, just to make it all pretty, n equals 1 to infinity of 3 times. And what I'm going to do is I'm going to bring these guys together so it looks just like a geometric series. So 3/4 to the n. And then, of course, there'll be minus the sum n equals 1 to infinity. And if you want, I could put a 1 here times 1/4 to the n. So then it's very clear. So therefore, this is a difference of 2 geometric series. And so in the first series here, my A is equal to 3, and my R is equal to 3/4. And the second geometric series, my A is equal to 1, and my R is equal to 1/4. Because now, what can I do? I can use that formula for a geometric series that if you have this sum, n equals 0 to infinity of A times R to the n, it's always going to be equal to A divided by 1 minus R. And so this will be equal to, we can write it here, this is going to be 3 divided by 1 minus 3/4. And then I'm going to leave some space here because there's something I want to talk about. And then minus, and this guy will be 1 divided by 1 minus 1/4. And now that's not quite right because notice where we start. We start at 1. We're not starting at 0. So if you start at 1, that's okay, but you got to take off the 0 term. So what we have to do is subtract off when you plug in 0 here for your n. So it's to take off 3 times 3/4 to the 0. And now that's correct. And over here, we have to take off, again, when you plug in 0, so like if you want 1 times 1/4 to the 0. And we'll put that one in parentheses because you're taking off the whole thing. And so now it's correct. And that's always a little bit tricky for you guys to see, but it's kind of like, here, this counts as 0 term. So really, when you write this out, it's A plus A times R plus A times R squared plus dot, dot, dot. And so this and this go together. But if you drop off this term, if that's not written there, it's no longer correct. So what you have to do is kind of move the term over to the other side, basically. So if you drop that term off, you can write it over there. And now the formula works if you have just the first term, if you just have this, basically that second term plus a third term and so on and so forth. Although in this, guys, when you have 0, it's like this is the 0 term, that's the first term, that's the second term. So what you'd really say is I only have the first and second because the 0 term was dropped off. All right. So hopefully that makes sense. If not, we'll work some more on it. So now I got to find the actual answer, though. So to find the actual answer, I have to do a little bit of arithmetic here. So my favorite way to simplify these guys is just multiply by 4 on top and bottom here. So this will be 12 divided by, and then this is going to be 4 minus 3. So that's just a 1. And then minus a 3, because 3/4 of 0 is just a 1 right there, right? Just gives you 1. And then minus, again, I just multiply top and bottom here by 4. And so I get 4 divided by, and then I get a 4 minus 1, so that's a 3. Put this in parentheses. And then minus, this is the 0 power, is just a 1. And so 1 times 1 is 1. And so that'll be equal to 12 minus 3. So 12 minus 3 is 9. So 9 minus, and I have 4/3, and then plus a 1, because the minus is going to go through here. And so that's going to be equal to 10 minus 4/3, which is equal to what? Well, 10 is 30 over 3. Minus 4 over 3, which equals, oh my goodness, what is that? 26? Yeah, yes, 26 over 3. And that's my answer. So there you go. All right, so difference of two geometric series there. All right, let's end this. All right, so we have one last little problem to do here, part B. And so part B, this is what's called a telescoping series, right? So it's a telescoping series. I kind of know that because right now I only know two types of series that converge, right? I know geometric series and telescoping series. We will learn about P-series. So there's another type of series called P-series that we can say whether they converge or diverge. And so let's just write out our first couple terms here because we're supposed to write out the first three terms, right? So let's be equal to, and so we plug in 1 because it starts at 1 again. So this is going to be 2 divided by, we'll go slow. So 1 times 1 plus 1. So 1 plus 1. And then plus 2 divided by, now plug in 2. So 2 times 2 plus 1. And then plug in 3. So you get 2 divided by 3 times 3 plus 1, which equals, oh, and then I need to write plus dot, 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 of course, right? Because it goes on forever and ever and ever. And so then equals, and now let's just do the math here. So this is 2 on the bottom, plus 2 divided by, and then down here you have 3 times 2, which is 6, and then plus 2 divided by, and over here you have 3 times 4, which is 12, plus dot, dot, dot. Then that's going to be equal to then 1 plus 1/3 plus 1/6 plus dot, dot, dot. All right, so there's the first three terms of the series. But now we want to figure out what it converges to. So on this one, what my brain is thinking, is thinking partial fraction decomposition. So it's thinking basically partial fractions. So maybe I can use what I learned about partial fractions, and this will help me solve this problem. So let's be equal to the sum n equals 1 to infinity of a over n, I'm not sure what a is, some constant, plus some other constant b over n plus 1. So there's this partial fraction decomposition. I need to find what a and b are. So remember how that works. So remember, these two things are supposed to be equal to each other. So what we can do is set them equal to each other, and that will usually tell us what our a and b are if we clear those denominators. And so we set them equal to each other. We clear those denominators by multiplying everything by n times n plus 1. So on this side, you just get a 2. On this guy, you get a times n plus 1. Plus, and on this guy, we get a b times n. And then we're just going to let n be different numbers. So, but we picked them nicely, right? So like, let's let n be equal to 0. Because basically, if n is equal to 0, this guy's going to go away. So that's going to imply that 2 is equal to a times 1, right? So you want to put 1 there, and then plus 0. And so that tells us right away that our a is equal to 2. So now we know what a is. And then for b, we're going to do the same thing again, but we're going to let n be equal to, and now n's supposed to be positive, but we can kind of cheat a little bit, right? Because we can make it negative. So let n be equal to -1. Let's see what happens. So 2 is going to be equal to, and then this guy is going to go away because it's -1 plus 1. So basically a times 0, right? Which is 0. Let's just write 0 there. So it's going to be 0. And then plus b times -1, which tells us that b will be equal to -2. And so this will be equal to what? This will be equal to the sum n equals 1 to infinity of 2 over n, and then minus a 2 over n plus 1. And so what we're going to do now is we're going to telescope this. We're basically going to write it out like expanding this like eye-seeing glass, like a telescope, and then we're going to contract it in on itself because it's going to cancel. So let's see what happens. So, we start here with n equal 1. So you get 2 over 1 plus 2 over 2. And then plus, now we'll let n be equal to 2. And so we'll get 2 over 2 plus, when n is 2 here, you're going to get 2 over 3. And then plus, now we'll let, and maybe I'll just write below that's n equals 1, n equals 2, and now we'll let n equal 3. And so what will happen now, we plug in 3 here, and we get 2/3. And then, oh, I'm missing the minuses, guys. Oh my goodness, to tell you what. I must be getting tired here, right? I'm sure you're getting tired too. We're almost done, almost there, right? So those should all be minuses. So minus, minus, and so plus 2/3 minus, and now I'm plugging in 3 here, so I have 2 over 4. And I kind of see the pattern. So without even looking, you can kind of see like, oh, the next one's probably plus, and I bet it's 2/4 minus 2/5. And then plus dot, dot, dot. So I expand out the series in some sense, and then check out what's going to happen. It's like, oh, minus 2/2 plus 2/2, minus 2/3 plus 2/3, minus 2/4 plus 2/4. Oh, they're all going to keep canceling. So they just kind of come back on each other. And so we just get the number 2. And so therefore, and let me come back here. Therefore, let me zoom out a little bit. I guess we don't need to write therefore if you don't want to, guys. So here, the series on this one, that series telescopes, and we get back the number 2. But if you want, we can write therefore, and sometimes I like to do this. Sometimes I write this as S. So therefore, S converges, and it converges because it is telescope, because it is a telescoping, and you can say it converges to, so let's write, therefore S converges to 2 because it is a telescoping series. Right, so on this section, it gets a little tough to do because you actually have to make conclusions every once in a while. You're fine right here if you just get it equal to 2, but we want to get in this practice of verifying our results at the end. So like even up here, when we did this one right here, we could write therefore our series, we call this S. So therefore S converges to 26/3. And we can even write because why? Because it is the difference of 2 geometric series. You might even want to say 2 converging geometric series, but we can start writing these conclusions, which just kind of ups our math game just a little bit. All right, guys, that was a lot, I know, but it's a good review of what we have done so far. So hopefully you were able to watch everything, and I'll see you guys after the weekend on Monday. Go have some fun with math.